So we're going to continue on with chapter 12 and the radical stuff. So there's two more reactions to look at that we're interested in that follow the radical type mechanism. So we're still in chapter 12 with our radical reactions. So the next one we want to talk about, it's called allylic halogenation. So when we talk about allylic is referring to carbon next door to a pi bond. And more specifically, a C-C pi bond. So if we think about a molecule like 1-propene, right, 1, 2, 3, so it would be 1-propene, then if we treat this with, let's say, bromine, and usually providing energy with an ultraviolet light source, what we're going to find is that this will provide us with a way to install a bromine on carbon 3. So we really haven't seen anything like this before. What's similar to the reaction we just looked at is this is also installing a halogen on an sp3 carbon. We really didn't have the ability to do anything like that before, but now we do, and so there it goes on carbon 3. So remember, whenever we're talking about a radical reaction, we split it up into initiation, propagation, termination. There's two propagation steps, which is really the key portions of the reaction. So let's take a look at the mechanism for this. So what I really want you to see as we look at these are really the similarities from one reaction to the next, to see really that all the radical reactions are happening in pretty similar ways. Okay, so then we'll begin with our initiation, and this will actually be identical to the initiation step we saw for the previous reaction. We start with our halogen, whether it's Br2 or Cl2, and we begin by breaking that bond between them. And remember, that's being broken homolytically to tell us that each atom takes one of the electrons. So we have these radicals that don't have any charge associated with them, but they are fairly reactive as a result. So then propagation will be broken up into two steps. And let's track it like we did before. Here I've made bromine radical. Now I'm going to consume bromine radical in propagation step 1. So here's my 1-propene. And what's going to happen, let me draw in the hydrogens on that allylic carbon. The bromine radical we just formed, it's going to take away one of those hydrogens to form HBr, and it's going to form an allylic radical where we were. So now there's a radical, and we formed HBr. So it's a little strange to think about resonance for a species with a single electron, but just to give you an idea here, right, if we want to think about this allylic radical, we can explain its stabilization through molecular orbital diagrams, but also what we can say is that the radical is delocalized over those 3 carbons. So usually genuine resonance structures, we move one electron pair, not electrons one at a time, but to show it for radical stability, that's what we need to do. And just like a carbocation is stabilized by resonance, a radical can also be stabilized by resonance. So then if we're tracking, like I said, we used the bromine radical here after making it in the initiation step. So now what we need to have happen in propagation is we need to make our product, but also make more bromine radical. So there's our allylic radical. Now we bring in another molecule of Br2. So this is still following the same pattern as the first mechanism we looked at. And so there you go, you're going to make the product, but also form more bromine radical. So then here's our product. Here's more bromine radical that has formed. So in that regard, it's the same pattern as before. What about for termination? Well, there are a lot of options for a reasonable termination step. The easiest one is just the opposite of initiation, where we say, well, if we no longer have bromine radical, then that's going to drop us out of the cycle of converting reactant into product. So that's one option for termination. We could also have the allyl radicals react together to make a carbon chain. That would also qualify as a termination step. So anything where the radicals are really getting quenched, that would qualify as a termination step. Let's see, how would this look? Like that. Let me number these carbons just to be clearer here, right? It should be a 6-carbon product because we're combining 2 3-carbon chains. So 1, 2, 3, 4, 5, 6. So that new bond, I'm not marking radicals, I'm just showing you the bond, would be between 3 and 4. And then the last option for termination would be making the product, but in this way forming the product by reacting 2 radicals together, which would drop us out of the radical chain mechanism that we were in, although that does make us product. So these are really just kind of the same pathway, just happening on slightly different molecules. So really something to focus on is just the pattern. And so here in termination, we use up the radicals. If I roll up a little bit, right, in initiation, I made bromine radical. Propagation 1, I used that radical. Propagation 2, I made more of the radical. And then in 2 of the 3 termination steps, I consumed that bromine radical. So that's the pattern that I focus on when I'm looking at this particular reaction. So here it's telling us that if we have a molecule with an allylic carbon and we introduce bromine or chlorine with the presence of a ultraviolet light to provide energy, that this is the pathway we're going to observe. And going back to the initiation step, that's where the light source really is needed, because we need to provide the energy to break the bromine-bromine bond homolytically. And so usually a light source will provide the energy needed to do that. Okay, so one more mechanism that fits into this category. This one has some similarities to what we've looked at before. The main differences are that we're going to have a 2-step initiation, and we'll be using HBr as our reactant, not HCl or not Br2. It's just this reaction only works with HBr. So let's backtrack a little bit, right, to our alkene addition. we know that if we take one propene and we react it with HBr, our expectation should be that we add to carbon 2, let me number here, 1, 2, 3, 1, 2, 3, and we know that this is a Markovnikov addition, right? It goes through a carbocation, etc., etc. So it turns out that at some point in time, someone did this reaction with HBr and somehow got the anti-Markovnikov product. So this just happens one time, and I forget which scientist was actually doing this, but the results were very confusing. And so then they went back to look at what happened, and what they found out is this was done from an HBr bottle that had been open for a little while. And so the conclusion was that there were some peroxides that had formed in the HBr bottle, and the presence of those peroxides was causing the reaction to go through a radical mechanism instead of the regular ionic mechanism. So a lot of times when we expose substances to oxygen, we'll start to have some peroxides that form. The peroxide you know probably the best would be H2O2, which is hydrogen peroxide. And if we look at the structure of that molecule, let me fill in the lone pairs, that's what hydrogen peroxide looks like. So just like you've seen us breaking the bromine-bromine bond, peroxides are good for taking us down a radical mechanism pathway because that oxygen-oxygen bond is really easy to break homolytically. In fact, it's one of the easiest bonds to break. So the conclusion was, in the old bottle of hydrobromic acid, some peroxides had formed, and that caused the production of peroxide radical, which drove the HBr to react in a radical pathway instead, and that was the explanation for forming the anti-Markovnikov product. So we'll look into that a little bit more to kind of figure out what's going on. Something important to point out, this only works for HBr, whether it's the energetics or the relative reactivity of the peroxide radical with HBr. Somehow it doesn't work with HI or HCl, but this is the one anti-Markovnikov reaction we have for an alkene to install a bromine. Remember, we have hydroboration to put an OH group anti-Markovnikov, but this lets us put a bromine anti-Markovnikov. So let's look at the mechanism for this reaction. Let me rewrite the reaction so we have it, and I'll use H2O2 as my peroxide. No guarantee that that's the one that was used, but I think now when we do it, that's typically what we end up doing. So this is not a Lilic, right? We're losing the pi bond and installing the bromine in the carbon 1. So make sure you're not confusing the Br2 reaction conditions with the HBr reaction conditions. Those are going to be different, but what you're seeing is anti-Markovnikov addition. So let's look at the mechanism for this one, and again, try to look at it from the perspective that there are similarities between this mechanism and the other two radical mechanisms that we've seen. Okay, so we'll start with our initiation as usual, and I think I said this before, it's going to be a two-step initiation rather than a one-step initiation. And what's going on, I'm just going to draw this flat. What's going on is in the first part, we're forming our peroxide radical. And that's what's happening that's so different in this reaction compared to the traditional HBr addition that's Markovnikov. So we form this peroxide radical, and then this is where everything is going to change, right? This is our second initiation step. The peroxide radical is going to react with our HBr, and that's going to form bromine radical as well as water. So in that two-step pathway, we've generated bromine radical, just like what we've seen in other reactions. So now what's going to happen is, in this case, we're going to have our alkene and bromine radical. And I think this reaction is conducted at higher temperatures. I'm going to flip around one propene just for convenience of our mechanism. So right here, it looks a lot like what we have going into the allylic halogenation. But like I said, I think this reaction is conducted at a higher temperature. So as with all of our propagation ones, this is a step where the bromine radical is getting consumed, but its consumption is leading to the production of a hydrocarbon-based radical. So the bromine installs at the end, giving us the radical on the secondary carbon, and that is taking place because, just like carbocations, we'd rather have a radical on a more substituted carbon. So it makes more sense for the bromine to be delivered to the outside so the radical can form in the more stable position. And that's the whole driving force for making this an anti-Markovnikov reaction. When the bromine adds, it adds such that we form the most stable carbon-based radical. Okay, then, right, propagation is always broken up into two steps. So now we've got our carbon-based radical, but it's already got the bromine installed. Following the pattern like we've seen for the other mechanisms, now the original reactant will be involved again, but in this case, the original reactant is HBr. So here, I'm going to get a hydrogen delivered to that secondary radical, so there's no more radical, that H gets delivered there, but I'm going to make more bromine radical. So this is what I focus on for all these mechanisms. Let me just rewrite that. I meant to highlight and just wrote in yellow. So there's our bromine radical. So following along, right, in initiation, even though it took two steps, I made bromine radical. In propagation 1, I consumed that radical that I made, and in propagation 2, we regenerate that radical. And remember, the whole idea is that we're cycling through steps 1 and 2, either until we run out of reactant, or the reactants drop out of the cycle in a termination step. So it should make sense that the propagation cycle itself looks sustainable. Okay, so then looks like I got to scroll down to the next page. Termination here. This will be kind of the same as usual. Our easiest option for a termination step is just, since bromine radical is our reactive species, just have two of those run into each other to form Br2, and then we won't be able to drive that process any further. The quenching of the carbon-based radical looks a little bit different here. I'll try to draw it like I did on the handout. So now we could imagine the two carbon radicals reacting together. My guess, just because of bulk, is that's kind of unlikely. And I'll number these after I draw it, just so we're clear what's going on. So let's number these 1, 2, 3, 4, 5, 6. So based on that, right, 2 and 5 are getting connected to each other. So let's translate our numbers over here. 1, 2, 3. Looks like I numbered the bromine. 4, 5, 6. So then here's our bond between 2 and 5. And then the last option, just following the pattern we have before, we've shown bromine radical reacting with itself. We've seen the carbon-based radical reacting with itself. But now we can have the two mixed together. We call this sort of step in a radical mechanism disproportionation, where the two unmatched radicals are reacting together. This will give us the dibromopropane product. So probably most of the termination, if we have it, is bromine radical reacting with itself, but these are our other two options as well. So that's what's going on with radical mechanisms. There are plenty more besides these three, but these are really the key three that come up the most often, so I wanted to show you those. And in this chapter, remember, we also talked about Hammond's postulate, which is kind of a far-reaching concept in organic chemistry in general, but the first place it really shows up in a useful way in the first semester class is when we talk about the selectivity of halogenation of alkanes. So that's what we wanted to talk about there. So my recommendation here is practice these three mechanisms till you feel really confident about what's going on in each one, focusing on what's similar between the three reactions. That'll be really helpful in this case, just so you don't feel like you're blindly memorizing three things, just kind of thinking about concepts that are similar within that. And then back to the previous video, make sure you can understand Hammond's postulate and the use of that idea to explain the fact that bromination is selective and chlorination is not. So yeah, that's it for chapter 12. So we'll call it on this video. When we come back, we'll be in our last chapter, which is chapter 9.